My name is Kesava Ramakrishnan. I'm a pediatric intensivist. Welcome to this video on ECMO circuit component. This is an illustration of an ECMO circuit used in a neonate in a VA ECMO configuration. In this case, the venous cannula is placed through the right internal jugular vein and is positioned in the right atrium, and the arterial cannula is in the carotid artery and placed in the innominate artery. The tip is placed in the innominate artery. The tubings conduct the blood from and to the patient. So this is the drainage limb, and this is the return limb, and this is the pump. In this case, a roller pump is used, which pumps the blood around the circuit. Gas exchange happens in the oxygenator. For the gas exchange to happen, a continuous supply of gas is required, and the gas blender here provides this continuous supply of gas to the oxygenator. A heat exchanger is also usually incorporated in ECMO circuit, especially when it is being used in small infants and neonates. The bridge is a connection between the return and the drainage limb. We will look at when and how it is used in subsequent slides. The ECMO circuit also usually has pressure modules for monitoring pressures at various sites in the circuit. A flow probe is missing from this circuit because this has incorporated a roller pump. If a centrifugal pump is used in the ECMO circuit, usually a flow probe is required. We will look at it as to why this is the case. There are two types of pumps that are used in ECMO circuits. The first one is the roller pump. Here, the tubing is compressed by rollers against a metal casing, and as the tubing is compressed, blood is pushed forwards. The main advantage of this kind of pump is that it is simple and inexpensive. Also, the flow is not dependent on the resistance. It can produce reliable flow. Flow is determined by the speed of the roller, the size of the tubing, and the length of the tubing that is compressed each time the roller goes around. As I said, the flow is very dependable, and it is not dependent on the resistance or afterload. Another feature of this pump is that the tubing is completely occluded at one point throughout. Even when the pump is stopped, the tube is occluded. This prevents any backflow of blood from the arterial side to the venous side. We will talk about this a little bit more when we look at the centrifugal pumps. The major advantage of this pump is that it produces very reliable flow, and you can calculate the amount of blood that has flown through the circuit by knowing the size of the tube, the length of the tube that's compressed, and how many revolutions per minute. A major disadvantage of this pump is that if there is an obstruction to the arterial line, for example, someone accidentally clamped or the line got kinked, the pump will keep pushing blood continuously, building up the pressure on the arterial side, which may lead to blowout. Similarly, if there is the intravascular volume is low and the pump keeps pumping, it may generate very negative pressures on the venous side, which may lead to entrainment of air. To prevent this, in most of the ECMO circuits that use roller pump, the venous drainage is usually passive and into a reservoir or a bladder, and the venous the pressure used for venous drainage is often determined by the height difference between the patient's bed and the bladder. The pump pumps the blood from the bladder continuously. If the pump pumps more blood than what comes in through the drainage, the bladder will start collapsing, which will then trigger the servo switch that slows down the pump revolution to prevent excessive negative pressure being applied. In worst case scenario, the bladder will completely collapse and the pressure will not be transmitted to the patient. The second type of pump that is used in ECMO circuits is the centrifugal pump. The centrifugal pump has an impeller which is placed inside a casing, and this impeller is driven by a motor which is usually situated within the console. The motor is coupled with the impeller by usually magnetically. As the motor drives the impeller, the blood column that is situated also starts spinning, generating a centrifugal force. This then forces the blood out of the casing through this outlet. As blood moves out, negative pressure is created in the inlet, sucking more blood from the patient. This pump is non-occlusive in that if you stop the pump and forgot to clamp the circuit, blood can flow retrograde from the arterial side, from the return cannula to the drainage cannula. This is because the pressure on the arterial side is always much higher than the venous side. If you stop the pump, you have to clamp the circuit to prevent this retrograde flow. The major disadvantage of this pump is that it is afterload dependent. So the flow varies depending on the afterload. Say if the resistance inside the oxygenator goes up or the patient's systemic vascular resistance goes up, for the same revolutions per minute, the flow would be much lesser. Therefore, the flow needs continuous monitoring and adjustment to ensure adequate oxygen delivery. Now let us look at some of the advantages and disadvantages of the roller pump versus centrifugal pump. As I mentioned before, the roller pump is not afterload dependent, whereas the centrifugal pump is afterload dependent. The inlet pressure in the roller pump is usually controlled by having a reservoir or a bladder, and the venous drainage happens by siphon effect. And the pump is servo controlled to prevent very negative pressures developing on the venous side of the ECMO circuit. This has not been incorporated into the centrifugal pumps yet. Therefore, they can generate very high negative pressures, which may be intermittent and very short, even microsecond duration, that can lead to hemolysis. You really don't need to monitor the flow when using roller pumps because they produce reliable flow. Whereas with centrifugal pumps, flow is required to be monitored continuously. Because the centrifugal pump has a pump head, usually the priming volume is slightly higher. Another disadvantage of centrifugal pumps is that they are more expensive. Centrifugal pumps allow retrograde flow, whereas the roller pumps don't allow retrograde flow because they are occlusive. There is a risk of blowout of the arterial side with the roller pumps. The risk is not significant with centrifugal pumps. Because the tubing is compressed continuously by the roller, there is risk of microemboli from the tubing. Extracorporeal life support organization data suggests that centrifugal pumps have been widely adopted. Only in the neonatal age group, roller pumps are still in use. However, I have to mention that there has been no clear randomized control studies which has shown benefit of one pump over the other. One of the advances that has happened in the ECMO is the development of hollow fiber type oxygenators, which have completely replaced the membrane oxygenators that were in use before. Most of the modern hollow fiber oxygenators are manufactured using polymethylpentane. They have the advantage of being plasma tight and also causing less inflammatory response. Usually the gas flows on the inside of the fibers and the blood outside. A major advantage of these oxygenators is that they do not provide too much resistance to blood flow compared to the previously used membrane oxygenators. This has enabled the use of centrifugal pumps um, as opposed to roller pumps. The oxygenators also usually incorporate heat exchanger. I will explain why this is necessary in the next few slides. An important concept to understand about oxygenators is the rated flow. The rated flow describes the oxygenating capacity of the oxygenator. It depends on the surface area and the membrane characteristics that are used in designing the oxygenators. The oxygenators come in different sizes, so it is essential to check the rated flow of the oxygenator and incorporate the right sized oxygenator in your circuit to ensure adequate oxygen delivery to the patient. The rated flow describes the amount of desaturated blood at a saturation of 75% and a hemoglobin level of 12 grams per deciliter that can be fully saturated, that is to 95% saturation per minute. To accommodate wide range of flow, the single lumen cannulas come in wide-ranging sizes from 6 French to 51 French. They are manufactured using biocompatible material and is often wire reinforced and may be coated with anticoagulants such as heparin. Percutaneously inserted cannulas are usually long and they have multiple fenestrations over longer segment at the end. Usually they may have end as well as side holes. Centrally placed cannulas usually have end holes only or may have a shorter segment of fenestrations, as only a small portion of the cannula is usually inserted into the blood vessel or the cardiac chamber. Also, centrally placed cannulas may have right angle tips or incorporate malleable wires so that the surgeon could shape the tip to optimally position them inside cardiac chambers. More recently, dual lumen cannulas have been designed which enable single site access for VV ECMO from jugular veins. These can be inserted by surgical technique or percutaneously. When appropriately placed, these cannulas can drain both from IVC and SVC, and the return line usually returns the blood to the right atrium as shown in this diagram. For this to happen, the tip needs to be placed in the IVC-RA junction or a little bit further into IVC depending on the type of cannula. It is important to appreciate that the tubing is also a very important component of the ECMO circuit. As shown here, if you use a half-inch tube instead of a quarter-inch tube, you could potentially increase the flow 4 times for the same pressure gradient. It is essential to have the tube big enough to allow free venous drainage with minimal resistance. The amount of gas that flows through the oxygenator every minute is called the sweep gas flow. It's measured in liters per minute. CO2 removal of the blood flowing through the ECMO circuit is controlled by the sweep gas flow. The sweep gas flow is equivalent to minute ventilation when we are using a mechanical ventilator. Oxygenation of the blood flowing through the circuit is controlled by the FiO2. The oxygen delivery to the patient depends on many other factors and will be discussed separately in a future video. The ECMO flow rates are very high. For example, the whole blood volume of a neonate could circulate through the ECMO circuit every minute. As the blood gets exposed to ambient temperature, the patient may lose a lot of heat and may become hypothermic. For this reason, heat exchanger is usually incorporated in ECMO circuits. Most of the modern oxygenators also incorporate heat exchanger within itself. A bridge is a connection between the return and the drainage limb, usually close to the patient. The bridge enables to separate the patient from the circuit in an emergency. For example, in case of air entrainment, the patient could be separated by clamping the drainage and return line, and the blood could be circulated through the bridge to the venous side so that the air bubbles are trapped in the oxygenator. Similarly, the bridge could be used to circulate the blood through the ECMO circuit during periods of trial off. For example, if you want to assess if the patient will be okay without ECMO, you could isolate the patient by clamping again the return and the drainage lines, keep the blood circulating through the bridge to prevent the circuit from clamping. This gives you an opportunity to assess the patient over a longer period of time to have more confidence in your decision making about decannulation. The bridge is only used in patients on VA ECMO. This is not necessary for VV ECMO, as the weaning is usually done by reducing sweep flow. A major disadvantage of having a bridge is that they become a potential source for development of blood clots. This is not an essential component and it's usually institutional preference. I have worked in some units where we have never used a bridge. As I mentioned before, with centrifugal pumps, the flow is afterload dependent and is variable. Therefore, it's essential to monitor the flow. This is usually done by incorporating an ultrasonic flow probe on one of the lines, usually on the return line. Also, most of the ECMO centers monitor pressures at various sites in the ECMO circuit. Usually, there is a pressure monitoring line to the venous drainage side before the pump. The pressure is usually negative here. It gives you an idea on how hard the pump has to suck to produce the flow that has been set. Most centers also monitor the pressure drop across the oxygenator. This is not so much of an issue now because most of the hollow fiber oxygenators offer very low resistance to blood flow. However, the pressure on the return line post-oxygenator could give you some information about the systemic vascular resistance or kinks in the return line. We will talk in a future video a little bit more about how to interpret these pressures. It is important to calculate the maximum flow that you may need with individual patients when configuring the ECMO circuit. You need to choose the cannulas, the tubing, the oxygenator, and the pump head that would enable you to deliver the maximum flow that may be required. Flow depends on multiple factors. Some of them are easily modifiable. For example, intravascular volume impacts on the flow significantly. So does the afterload. If the blood pressure is too high and the systemic vascular resistance is very high, the flow may be less than optimal. It is possible to use vasodilators to reduce the systemic vascular resistance, which will encourage the ECMO flow and oxygen delivery. Another easily modifiable factor is the speed of the pump. You can just increase the revolutions per minute, which will increase the flow for a given resistance across the circuit. However, there are many not easily modifiable factors, such as the vascular access site, size of cannula, the length and the diameter of the tubing, and so on. This is why you need to think carefully about the circuit components so that you are not in a situation where oxygen delivery is compromised. I really encourage you to find a picture on the internet and see if you can identify the different components. Thank you.